Warm up, everybody, everywhere. Okay, so we got the g of x is e to the 3 times the inverse tangent of x squared. So this is exponential, right? And we're doing this in pre-cal right now, right? We know it's exponential because number one, we have a variable in the exponent. That's the first important part. And then number two, we have a number in the base, right? And although it looks like a letter, this is a math class, so we know in this class, E means what? 2 point is good, right? Enough. 7, 1, 8, yeah, dot, dot, dot. People celebrate Pi Day on March 14th. People celebrate E Day on February 71st, which we calculated last period was like March 12th or something. Yeah, on the leap year, it's on March 11th. Okay, so anyway, what is the derivative then of e to the blob? No. E to the derivative of e to the blob is e to the blob. The same thing, right? Do I need to play the song again? Okay. And then times, if we wanted to use the general rule, it would be times the natural log of the base. But do we need to do that here? We can, right? That's what you would do every time, but this is the only time that we don't need to because the natural log of e is 1. And so e is the only exponential function that is entirely its own derivative. Every other exponential function is a vertical dilation of itself by a scale factor that is the natural log of the base, okay? But we do have to concern ourselves with the chain rule. So we'll get rid of all this stuff. There we go. Times, now the derivative of 3 inverse tangent. Well, 3 can go along for the ride, and the derivative of inverse tangent of blob is 1 over 1 plus blob squared. And what's that blob? That blob is x squared. And now we have one more link in the chain rule, right? Times the derivative of the innermost blob, which is the derivative of x squared, which is 2x. So we did have 3 layers, the e layer, the inverse tangent layer, and the x squared layer. And now we have 3 links in the chain, purple, red, orange, right? Orange kind of looks like the red. Yeah.
So do we have to write the natural log of e or a 1, or can we just?
No, you don't even need that there. No. I just put that there kind of as a review. Yeah, that could be gone, right? There we go. And that would be the derivative, right? We'd be done. You can clean it up. Now, let me change the problem since we can all do that easily with notability. All right, let's change the E to a, let's change it to a 4. It's not going to change much, is it? It's still exponential, right? It has a variable exponent and a numeric base. What would the derivative of 4 to the blob be? 4 to the blob times the natural log of 4 times everything else is the same. That's really the only thing that changes. I'm going to color code that. We'll do that in blue. If whatever that is, that's whatever this is. Okay. Let's change it from a 4 now, from a 4 to, let's change it to, a 1/2 is what I was thinking. Now that's still exponential. You would need the parentheses around the 1/2, so you would know that the 3 inverse tangent is part of the whole thing, not just the 1. So what would be the derivative of 1/2 to the blob? Well, it would be 1/2 to the blob times the natural log of a 1/2, and then times everything else is the same. You got the idea? Okay. You know everything there is to know then about derivatives of exponential functions, whether they're base e or base other than e. All right, let's go put it back in terms of e, and then we'll simplify it. That's a good idea. Okay, I'm not even going to put natural log of e there. I'm just going to get rid of that, and again with notability, it's easy to remodel. Okay, so if we're going to clean it up, this factor here in the front, the e part, it's ugly, but that's like 3 over 1. That's like 2x over 1. So if we just rewrite this part, inverse tangent or arctangent, right? What can we call the next factor? Well, 3 times 2, that we can call that a 6x in the top, And in the bottom, that's 1 plus x to the fourth. So that would be one version of it. The other version, since that is e over the 1, is you could put all that in the top. Maybe write that as 6x e to the 3 inverse tangent of x squared all over 1 plus x to the fourth. That's another version of it. Okay, that's just the algebra part, the manipulating of the symbols on the back end of it. Yes.
Okay, for your response, could you just leave the top line?
Uh-huh.
But that's the qualified answer.
Yeah, let's talk about a free response. That's good. How would you know how far to simplify a free response? Well, if you've answered the question, if it just said find g prime of x, or you needed it for something, you're done. Here's what a lot of the time happens though on a free response. It'll say show that g prime of x equals, and then it gives you the final form that it needs to look like. And so what you would do, let's just say they had this in there. Show that the derivative equals that. You know what the answer is now. So it serves two purposes. What it does is it allows them to test your ability for taking the derivative, as well as showing enough algebraic steps on the back end to get to the answer. You would have to show like at least one algebraic step in between, like this one here. All right, so that's how you know then I need to go to this step. And then the other reason they do that is if you're unable to find the derivative on your own, let's say you forgot or you tried the power rule when it was exponential, you can use their derivative that they give you to answer the rest of the parts of the question. So you're not double penalized. So yeah.
So check wise, it'd be like that first line would be one check, and then the final line would be another check.
Yeah, if this were like get to the final form, you would probably get 2 checks for the derivative, believe it or not. One for the e part and one for everything else. And then you would get 1 part for getting to the final form with just, it's really just 1 step in between, but the cleanup step, showing that the 3 times 2 is a 6. Usually there's a more significant step in between. So this is not necessarily the best example, but yeah, the algebra would then be worth a check. Okay. All right. So let's go ahead and see if we can, we'll finish here probably easily before lunch. So here's the chart, the general derivative of b to the x, where b is any base. It's b to the x times the natural log of b. Don't forget that scale factor. And then, of course, as we just saw, if x is u, some differentiable function of x, then the derivative of b to the u is b to the u natural log of b times u prime. Instead of u, I called it blob, but it's really the same thing, right? That's the chain rule built in. All right, let's try it out then in some applications. At what point on the graph of y equals 2 to the teeth power minus 3 does the tangent line have a slope of 2? All right, so you don't have to do what I'm about to do, but I'm going to do it just for the sake of kind of visualizing what it is we're asked to do. 2 to the t is your exponential growth parent function, right? It looks just like e to the t or e to the x. What does the minus 3 do to that graph in any graph when you do that in the equation? Shifts it down 3. Now, what significant feature of the graph does that move? It moves the y-intercept, but what does, yeah, the asymptote. There's going to be the asymptote, which was at y equals 0, is now at y equals -3. That's a significant piece of it. You can always find a new y-intercept. The y-intercept is not necessarily a point that you have to track, because you can always come back and find a new y-intercept by plugging in a 0 for t. What would that be? 2 to the 0 is 1. 1 minus 3 is it's -2. So for what it's worth, here's what the graph looks like. And remember, exponential functions are interesting because they have dramatically different opposite end behaviors, right? On the one end, those terms go to 0, and on the other end, they go to infinity. All right, so we want to know where the slope is 2. So I don't know where it is, but if I drew it to scale, which I doubt I did, it might be right there, right? Let's say that this line has a slope of 2, and we're trying to find what this point is, right? X, Y. That's what we're looking for. Bless you. All right, so if you can visualize it in your head, that's great. You do need a plan of attack. What's our plan of attack then? How do I answer the question? I want to know where the slope is 2, so that's where the derivative is 2, right? So we're going to need the derivative. So because it's explicit, we don't need to put d dx, but if you want, you can always put d dx. The left side becomes dy dx, and the right side becomes, what's the derivative of 2 to the teeth power? Oh, I said with respect to x. It's actually with respect to t. Good catch there, guys. What would be the derivative of 2 to the teeth power? 2 to the teeth times the natural log of 2. Good. Boom. What would be the derivative of -3? 0, right? We can just go term by term. Okay, so there's your derivative. Yeah, that was easy. Now we set it equal to 2. Right? You always show the equation you're solving. So you would get a check. Let's just always talk about, free response. You'd get a check for the derivative, and you would get a check for showing that you're setting it equal to 2. And then you get a final check for finding the t value. So now it's just algebra, right? We got to peel back the layers and get at the t. So the first thing I need to do is get rid of multiplying by ln of 2. How do we undo multiplying? Divide. So I'm not going to show it, but if I divide the left side by the natural log of 2, it divides out. And if I divide the left side by the natural log of 2, I get 2 over the natural log of 2. Oh boy. Now, how do I unexponentiate something? The teeth root, that doesn't quite work. It has to be a numeric root. Logarithms. Yeah, I didn't hear it. Yeah. Logs. Now, if you wanted to, since it's base 2, let's look at it 2 different ways. You could take log base 2 of both sides, and that would be written in the front. Okay. Log base 2 of both sides. I'm going to put a different color on that just so you can see the similarities. Okay. So then that would be 2 to the teeth, and then 2 over the natural log of 2. Now, the reason that's nice doing log base 2 is because what is log base 2 of 2 to the teeth? It's t, right? When you compose 2 inverse operations back to back simultaneously, you get your input. Start with t, exponentiate at base 2, log at base 2, you're back where you started. And now you really wouldn't need to simplify this side. If this were like a free response, there's your t value. All we'd have to do is find the corresponding y value, okay? Now, if this were a multiple choice question, they're probably not going to have it in terms of base 2. I doubt they would. They usually put everything in terms of the natural log. So you could keep going with this vein, but you'd have to use the change of base formula. Y'all remember the change of base formula? Let's review the change of base formula. If you have log base b of x, it's going to be the natural log of x over the natural log of b. Or you could choose a third party base. A third party, I'm exhausted. I can't fathom going to another party. But okay, c'est la vie. Right? Hey, yeah, I should have just kept that to myself. I always, a third party, I don't know. Third party. I would never go to a third party.
Never? You don't party hop?
No. I'm usually passed out at the first party. Just exhausting, that's what I mean. Just too much. That's right. Too much dancing, too much Trivial Pursuit board games. I crash right there at the table. Yeah. Right. Oh, A is just a random other variable. So in other words, I can choose whatever base I want. If I don't like base B, choose base 72, right? So look, here's an example. If I have log base 3 of x, I can write this as the natural log of x over the natural log of 3. That's choosing base E. And that's typically what we're going to do. But just an FYI, let's choose base 42, right? That's the answer to everything. This would be log base, bless you, 42 of x over log base 42 of 3. It can be any base. Okay, just an FYI. So it's really the log of the argument over the log of the base. So it's easy to remember which one goes on the bottom because base goes in the bottom, right? All right. So if you wanted to now, that's the change of base formula. You could change this and write it as the natural log of 2 over the natural log of 2 all over the natural log of 2, right? That would look like this, the natural log of over the natural log of, and that would be 2 over the natural log of 2 all over 2. Yeah, that is a lot of natural logs. And That might be the answer, but I doubt it. They're probably going to have a simplified version of that. The properties of logs allows you to write things in so many different equivalent forms. And that's why a lot of people hate logs. But if you're good at logs, that's kind of what wears you out at the first party. When you're at the math party playing with logs, you don't make it to the second party because you play with logs until you have no more energy left, right? So that would be, and we can keep going with that, but I want to show you the other way to do it where you don't have to keep manipulating it. Once you have this step, you could just take the natural log of both sides, right? Just go straight forward with the natural log of the left side and the natural log of the right side. All right, so this would be 2 to the teeth power and 2 over the natural log of 2. Now, on the left side, unfortunately, it doesn't just collapse straight down to t, because logging base e and exponentiating base 2 are not inverses of each other. But guess what we can do using one of the properties of logs? I could bring the t out front, and that turns then the natural log of 2 on that side into a constant multiple. And now how do I solve for t? If I'm multiplying by ln of 2, divide both sides. Okay, so I get the right side, which is the natural log of 2 over the natural log of 2, all over the natural log of 2. And oh, by the way, that's the same thing we have over here. So maybe that is the answer, but I doubt it. Here's why I doubt that would be a multiple choice answer. It has that complex fraction feel to it, right? You got like a fraction in the numerator of a fraction, and that's like yucky, yucky, gross, gross. So let's review 2 more properties of logs. Hello, Hillary. We have this one that says the natural log of x times y is equal to the natural log of x plus the natural log of y. A log turns a product into a sum. The natural log of x divided by y is the natural log of x minus the natural log of y. It turns a quotient into a difference. The denominator gets the minus sign. And then for what it's worth, we could say the natural log of x to the n is n times the natural log of x. So that kind of puts them all together. Now, keep in mind as well that these identities, if you will, these properties of logs, they work both ways. When you go from left to right, we call that expanding. And when we go from right to left, we call that condensing. You might have done that in algebra too. It's like playing an accordion, not unlike Alex Mikeson. See you, Eliana. Dun, 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 dun. Okay, so here's what we could do in the top. I have the natural log of a quotient, right? So I can actually write that as the difference of 2 logs. So it's going to be the natural log of the numerator, the 2, minus the natural log of the denominator, which is the natural log of 2, all over the natural log of 2. So that second term in the top is now composition. All right, so that looks a little bit better already, right? Now, if you're a pre-cal student and you got this far, you might go, ooh, ooh, ooh. But yeah, you don't want to mess up here at the end. But notice you could split up the terms now, right? You can call it the natural log of 2 over the natural log of 2 minus the natural log of the natural log of 2 over the natural log of 2. And now you could go, ooh, ooh, ooh. And that does become 1, but you're left with this. And I'm not sure we can simplify that anymore. So what would be a multiple choice answer? Well, this doesn't look half bad, nor does this look half bad. So yeah, I don't know. You'll kind of see that throughout the year when we get answers that have logs in them, we kind of coochie coo them on the end. We play with them quite a bit. Peekaboo, peekaboo. All right. So we can practice our skills of manipulating expressions with logs into synthesizing them, if you will, into equivalent expressions. All right. Free response, though, you get t equals, boom, and you're out of there, right? T equals this right here, free response, you are Brooks and done. Under a neon moon. All right. Now, if you needed to find the y value that went along with it, all you'd have to do is plug it back in right here. So perhaps I should rewrite the question at what value of t, right? Because finding the coordinate is just an exercise in cumbersome writing. It would be that value, right? Let me write it like that. The natural log of 2 minus the natural log of the natural log of 2 all over natural log of 2, comma, 2 to all of that power minus 3, right? Yucky, yucky, gross, gross. So you wouldn't have to do something that disgusting. It would probably say find the value of t for which that has a slope of 2. Okay, so that's a nice application. And we got to review properties of logs. Hey, while we're here with the natural log, let's go ahead and throw this in here too, just so it's all in one place. E to the natural log of x equals x, which equals the natural log of e to the x. That gets used quite a bit too. We talked about that last time. So good so far, so good. Comments, questions, quick shows, concerns, good clean jokes. Where can you find a turkey with no legs? Right where you left it. Yeah, good. Yeah, very good. Yeah. All right. Yeah. I guess it'd have to have no wings either in your meat freezer. Yeah, very good. Very good. It takes like 42 days to like defrost like a 42-pound turkey. Like a pound a day, I think is the defrost rate. So I hope you started already with yours or something like that. I'm not allowed in the kitchen. Okay. 42 hours. Oh, an hour per pound, not day per pound. That makes more sense. Oh, I was going to say, here we go. Yeah, Betty Crocker over here.
I think at least half a day.
At least half a day. You don't just throw a frozen turkey in the microwave for 5 minutes and say, hey, everyone's here.
I mean, unless you want to throw in the deep fryer frozen.
Hank, is that what goes on at the second party? Because I may try to kind of save some energy for the second party. I've never been to a third party, so I wouldn't know. But maybe at a second party, I would kind of.
According to the USDA, they recommend that for every 4 pounds you weigh 1 day.
Okay.
So it is like 4 pounds for 1 day. I know it's a long time, yeah, because it happens in my house every year, and I'm just like, is it ready yet? And they're like, no, it's still like 4 days away, and I'm like, okay. That's right, yeah. Well, you defrost it in the refrigerator head of the door. You don't you can leave it out on the counter, but you put it in the refrigerator. Yeah. So when it's finally thawed, it's still cool. Yeah. No, I mean, you can put it on the back porch, and if the dogs lick it, every hour, it defrosts faster, right? Yeah. Letter A, we're on example 5. Letter A, evaluate the following. We're in verb format now, right? DDX of. Well, I have a numeric base and a variable exponent. Is this going to be the power rule? No, this is exponential rule, right? Exponential is always variable in the exponent, numeric base. So what is the derivative of 7 to the blob? 7 to the blob times the natural log of 7. Very good. That's that first layer times the derivative of -3 over x. Now, notice I didn't take a whole line to rewrite -3 over x. So what I might do, if this were truly a free response, is come off to the side on my workbench and just write -3 divided by x as -3x to the -1st. Just to help me, right? I don't want to have to use the quotient rule in the exponent. So bring the x to the top, and now, it's a lot more informal on the workbench. I'll draw an arrow to show that I'm finding its derivative. Multiply and subtract, yes? So that would be a +3x to the -2nd, right? And now you can bring that in here, or you can say, hey, since I'm right here, let me just rewrite that as +3 over x squared. And now it looks a little bit prettier, right? So you don't have to go vertically and have all of the steps of every little piece being simplified. But if you do, it has to be equivalent all the way down. You're allowed to go off and compartmentalize and then bring results back in to your project. So yeah, is there a better way to write all of that? Probably not much, right? You can put the 3 natural log of 7 in the front times 7 to the -3 divided by x all over x squared. That's about as maybe good as you can write it. The 3 natural log of 7 would naturally go together because those are your numbers. Now let's think about 3 natural log of 7. That's probably how it would be written, but is there another way to write that? Seven to the third. Now that goes against what logs are designed to do, right? Logs are designed to make molehills out of mountains, not mountains out of molehills. But it would be equivalent. If that were like a smaller number, like maybe 7 squared, then maybe a multiple choice might have the natural log of 49 there. But 7 cubed, they're not going to make, they don't expect you to know what 7 cubed is. And they're not going to make you go off to the side and do, retro stack multiplication. So anyway, but it's good to think about it, right? Oh, hey, speaking of, look what else we can do. It's all just one big term. What if I brought 3? What if I did that, and then I did this, and then I did this? Now, could I bring this whole thing up as an exponent? We're playing with logs. This is why I never make it to the second party. Right? So that is equivalent right there. Yeah. Yeah, that would work. Yeah. I mean, does that look? No. Well, no, that doesn't look good at all, but it's equivalent. So when we have logs, we explore equivalent versions, whether they're going to happen or not. It helps us to become proficient with manipulating things, right? Mental agility. All right. All right. Letter B. E to the natural log of x. Okay. So that's the verb form. So it's e to the blob, right? We have a numeric base and a variable in the exponent. It's exponential. What's the derivative of e to the blob? E to the blob, right? Times the natural log of e. Do we need that? No. I'm my own grandpa. I'm my own grandpa. It sounds funny, I know, but it really is so. I'm my own grandpa. All right. Times the chain rule, the derivative of the natural log of x, which is what? Next chapter. Oh, okay. We don't know what the derivative of the natural log of x is. What the heck is this doing in this chapter? No. Natural log of x is not his own grandpa. Simplify. Right? Simplify early and often. Simplify early and often. What is e to the natural log of x equal to? It's equal to x, isn't it? Yeah, recall up here, right here, right? Remember, e to the natural log of x is x. So is natural log of e to the x. Now, when you get excited because you notice that on your own, and this were a multiple choice question, guess what answer choice A is going to be? X. You're like, oh, I saw the inside. It's X. Ooh, bubbly. I'm on to the next. Bang. But what have we forgot to do? We forgot to bust out the calculus, didn't we? Yeah. It's like bust out the algebra. Yeah, no, that's not worthy of a shirt. This is why you want to make sure you bring the instructions along with you, right? ddx of that is the same as ddx of that. And now you're like, oh, what's the derivative of x with respect to x? 1. And that's probably answer choice E, right? Or it could be A. I'm not saying that A is always the wrong answer, but a lot of times psychologically they build a test like that, No, A could be correct. All right, letter C. Notice our variable has changed from X to T. No big deal. Do you want to FOIL this out first before we take the derivative? Is that necessary? Yeah, we could, but would that be simplifying it if I make 3 terms out of? Yeah, I wouldn't expand it because we know the chain rule, don't we? So when you walk up to this problem, you're like, what's up, blob squared, right? There's your first layer. And then you go inside, and the next layer is these 2 terms, e to the negative t plus e to the t. Now, notice the first term also has its own miniature chain rule going on. So let's do the derivative. Nothing needs to be rewritten. The outside layer is 2 blob to the first. Right, there it is. That's how I write it, 2 blob to the first. And then we just rewrite the blob. Times the next link, parentheses. Get in the habit of doing times parentheses, right? We absolutely need it here because it's more than 1 term. And now we take the derivative, we unpack the boxes as we get to them. What would be the derivative of e to the negative t? E to the negative t times natural log of e, which we don't need, times -1. Yes, this is so commonly missed. I don't know why. Students know the derivative of e to the x is e to the x, but when they say e to the negative x, they think it's e to the negative x. It's not. It's if your inside function is ever more than plain old x or plain old t, it's a chain rule.
They got too much differential.
That's what happens at the third party.
Too much differential.
Yeah. Plus, what's the derivative of e to the t with respect to t? Just e to the t, right? Boom. And there's your answer, right? There's your answer. Now, let's say that this is a multiple choice. That's probably not going to be your answer choice. So let's go ahead and tidy it up a little bit. We got a 2, and I'm going to go ahead and, well, we'll do more than one step. Maybe we don't see the insight yet, but that negative that's multiplied out behind it can actually go in front. E to the negative t plus e to the t. Now, who likes to lead with the negative? Not I, okay? So what would probably happen then is in that second term, we would commute those and call it e to the t minus e to the negative t. Now, in the first term, because the e to the negative tth term is in the second slot, we might also commute those, although it doesn't really bury a negative sign. It does kind of make the two terms coincide with each other. And now that probably will not be an answer choice either, simply because this is a special product. Those two guys are what?
Square.
Yeah.
They're perfect squares.
Their product will give you a difference of squares. Good, because these two guys are what conjugates? Conjugates. There you go. They're what conjugates. Let's go ahead and multiply. Let's go ahead and multiply it out. E to the t times e to the t is what? E to the 2t, not t squared. E to the t times e to the t is e to the 2t. Okay, now your inner and outer terms you don't need, but I'm going to go ahead and do them just because they're kind of interesting. What is e to the negative t times e to the positive t? Remember, we're adding exponents. So what's negative t plus t? 0. And what's e to the 0? It's really 1. So we get a +1 on the interior. And then on the exterior, we get minus, what's e to the t times e to the negative t? E to the 0, which is also 1. Now they both simplify to 1, but they're opposite signs. So they do in fact cancel. The inner and outer will always cancel on the two conjugates, but it was kind of interesting to look at it. So now we have a positive times a negative in the last position. So it's negative e to the, and remember when the bases are the same and we're multiplying, we add the exponent. So it's e to the negative t times e to the negative t, e to the negative 2t, right? Right. And now if we simplify, we get 2 times e to the 2t minus e to the negative 2t. There you go. That would probably be the answer. So a lot of algebra, right? Calculus takes one line. That was the very first line. And then some algebra. All right. Wow, look at D. Oof. Let's say we don't simplify D. I wrote D just for the sole purpose of seeing if you could do the derivative. So I'm gonna let you do that one while I go Google how to do it. Okay, I'll be right back. I'm gonna pause the recording too. Yeah, go for it. Don't simplify it. Just take the derivative and stop. We do this. I'll resume recording. Okay. So first and foremost, it is a product rule. So with two factors, we're going to get two terms. So the derivative of the first is 2x times the second one just goes along for the ride. So that's 5 to the sine squared of 4x power. That one's not that bad. Okay. Plus, now the x squared gets rewritten, and now it's time for the second factor. So when you go inside the second factor, the first layer that you see is 5 to the blob. So it's going to be 5 to the blob, which is sine squared of 4x, times the natural log of 5. That's still part of that layer, okay, because it's not base e. All right, then I can go up to the exponent, and the first layer I see there is the one that people typically miss. Because notice I've been writing it in the condensed form down below, but if you don't ever write it in the expanded form or realize it, it's the one that people miss. So that would be then times 2 parenthesis to the first. And that would be the blob right there, sine of 4x. And then times, I go inside to the aquamarine level, which is sine of blob, and that becomes cosine of blob. And then finally, the innermost blob is my gray blob. The derivative of 4x is 4. And if you really wanted, you could say that x is inside itself times, let's get in on the action, the derivative of x, which is dx or 1, which you don't need to do, okay? So it is kind of cool to notice, oh, and then we close the whole thing, right? That as you do that, the pieces get smaller and smaller, right? There's that one, then that one, then that one, then that one. That's going to be very important when we start going backwards, because the chain rule unpacks the boxes and integration packs them back up. And there can only be one big box. So if we were going backwards, this piece here would be the big box. And everything else would package back up. This would go back inside there, and then that would go back up inside there, and then all of this goes back inside there. And then we integrate the big box, okay? In other words, the original rule was the exponential rule, and that's how we got that first red factor. But that's just kind of thinking ahead, all right? Yeah, it does, right? It does. It sure does, right? All right. So if you could do that, you're in good shape. All right. And then the last one right here, take about take 30 seconds or so and do that one. There's a big glare over here. Hard to see screens. Don't put DDX equals because it's verb form. So you just evaluate it and the DDX goes away. Yeah. Right. Unless you're rewriting it, then you still have DDX of. So you did the product rule, right? So this is itself, but then how'd you get a 1? It would be times. Oh, okay, but if you did the derivative of e to the blob as itself, then you would need to multiply by the derivative of the blob. What would be the derivative of 3? 0, and that would wipe that whole term out. Yeah, and so there's your answer. Yeah, yeah, because really e cubed is just a, yeah, there you go. Kenya's got it. Kenya's got it. Okay, so the point of this question is to illustrate that just because it has e in it doesn't mean it's an exponential function, right? If you look at this piece here, that's just the number, right? It has the numeric base, but there's no variable up here. So if e is about 3, right? If e is approximately 3, then e cubed is just approximately 27. What would the derivative of 27x be? Yeah, you wouldn't hesitate to say it's 27, right? So what's the derivative of e cubed times x? E cubed. It's just the coefficient of a linear term. Now, you could get there another way. Watch. I heard some of y'all saying, is this the product rule? And yes, we have special holidays throughout the year called elevate constant multiples to their own function status in the product rule day.
My grandfather practiced.
Yeah, yeah. Right after Toyotathon's over, if you've got any steam left, right?
That's the fourth party. Yeah.
What would can you believe I grew up next to a guy that never celebrated Toyotathon? Hmm. The derivative of e cubed is itself times the derivative of the exponent, which is 0. X goes along for the ride, e to the cube, and then 1. So that would wipe out that whole first term and you get the same answer. So size up the problem carefully. Just because it has e doesn't mean it's a variable exponential factor. All right. Have a great lunch and we'll see you afterwards.
We're already late.